Assalamualaikum everyone, my name is Asma Amira binti Muhammad Alwi, and today I will be presenting to you about the application of differential equation and its solution using Mathematica. This presentation is a part of my individual assignment for subject computational techniques in mathematics. It explores how we can model the cooling process of a hot object using first order differential equation. Without further ado, let's watch the video.
For the introduction, Newton's law of cooling describes the rate at which an exposed body changes temperature over time as it moves toward the ambient temperature of its surrounding. It is a first order differential equation. For the problem statement and literature review, the problem in this study involves a freshly brewed cup of coffee that is left to cool in a room. The aim of this study is to model the cooling process of the hot coffee using Newton's law of cooling. As we know, Sir Isaac Newton was the first person who formulated Newton's law. He assumed the rate of loss of heat from a body is directly proportional to the difference in the temperature of the body and its surroundings. Methodology. As you can see here, this is the general formula used. So T time is temperature of the object at time t, Ta ambient temperature, T0 initial temperature, and K cooling constant. We made several assumptions in this model. The environment has a constant temperature, there is no internal heat generation, and there is no phase change in the object. The output graph confirms the expected behavior. At T0, the coffee starts at around 90 degrees Celsius. The temperature decreased rapidly at first due to the large difference between the coffee and room temperature. Over time, the graph flattened, indicating that cooling slowed down. Eventually, the coffee temperature stabilized near 25 degrees Celsius, which is the ambient room temperature. This matches the idea in Newton's law of cooling, which states the greater the difference in temperature between the object and its surrounding, the more rapidly the heat is transferred. So, we can conclude that Newton's law of cooling effectively models real-life temperature loss. The graph confirms that cooling is fastest at the beginning, then slow down as the coffee cools until it stabilizes near room temperature. Using Wolfram plot make it easy to solve the differential equation, visualize the temperature change, and understand the real-life application of the mathematical model. Here are the references I used for this project, including online tools and educational sources. And hereby, that concludes my presentation on Newton's law of cooling. Thank you for your attention.